Well, thank you to the organisers for the opportunity to be here and speak to you, and thank you to all for such a stimulating conference so far. It's been, especially the plasma side of this community is not one that I interact with anywhere near enough. So it's been extremely interesting to be here. So I want to tell you about aspects of turbulence and variability, turbulence in black hole accretion disks. And in a sort of nice complement, and this wasn't planned, but nice complement to Omar's talk, I'm actually principally going to be thinking about these kind of systems. So black hole X-ray binaries, where you have a quote normal star feeding matter onto a stellar mass black hole. So fiducial mass would be a 10 solar mass black hole. I'm going to try and define my jargon here for because I know that this is a very multidisciplinary audience. In particular, there's low mass X-ray binaries. The low mass is the star, not the black hole. It's the star that you're feeding matter. And there's a whole pile of phenomenology which comes with that, which I won't get into. So I want to focus in this talk on connecting the data aspect, the observed phenomenology of some of these systems, into aspects of the MRI-driven turbulence paradigm we have in accretion disks, and see whether we can make some connection points there between the actual data and some of the aspects of the theory. So first, I want to introduce, understanding that this is not fundamentally a black hole audience. I wanted to give you an insight into some of the phenomenology, actually some of the observations of these systems. This could easily be many-hour talk, but just to touch on some of the principal things. First and foremost, the spectrum, the energy spectrum of this is a representative, as you'll see in a minute. This is certainly not the only form of the spectrum. So the X-ray spectrum from say half to 10 keV is typically a broadband spectrum, and we often attribute at least two components to it. There's a soft black body-like component that we believe is coming from the optically thick, your highly collisional accretion disk that is extending from some region close-ish to the black hole outwards, of order 10 to the 7 Kelvin. And then on top of that, there's an X-ray tail, a power law-like tail that we believe corresponds to inverse Compton emission of that softer black body emission by some distribution of hot energetic electrons, so 10 to the 9 up to 10 to the 10K electrons in some distribution that we generically call the corona. And it's inverse Compton scattering in the corona that's giving us this emission here. And then there's other features. On this plot, there's a little bump here, which is a broadened ion emission line that careers have been built on. Looking at what that structure tells you. But that's an example of the spectrum. Now, a key aspect of these systems is, you'll see in that plot there is said high state, or sorry, it says hard state. These systems undergo state transitions. So the aspect of these low mass X-ray binaries is they go through outburst cycles. They can come literally from nowhere. You can have a system that's completely unknown in quiescence. So the space to look at is X-ray luminosity versus X-ray color, hardness. So sources that are dominated by high energy X-rays are at the right here. They can literally come from nowhere. They increase in luminosity in a hard state. They then undergo quite a rapid transition to the soft state, then they can dim, and then they can go back. This whole cycle can take of order weeks to go through, which is forever in the life of an X-ray binary. And the other key thing is this is hysteresis, that thinking that roughly the y-axis here, X-ray luminosity, is basically mass accretion rate in the inner disk, the radiating part of the inner disk. Then the transition from hard to soft is at a different accretion rate than soft to hard. So what generates that hysteresis? Now, this is from a nice article by Jinghe Wan. This is how the spectrum changes as you go through the cycle. So this is the spectrum I just showed you. Then as you transition to the soft state, basically what happens is that quasi-black body thermal part just races up. The disk gets hotter, it gets brighter. And at the same time that X-ray tail, the inverse Compton piece, dims and gets steeper, and that's what's driving this soft spectrum. Now, hand in hand with that, there is very non-trivial behavior in the variability systems. So these are power spectra, and just for Sasha's benefit, I made labels nice and big here. And so this is the example label that applies to all the power spectra. There's power spectra here. So in the hard state, you have a very variable system. I'll pull apart the power spectrum just in a little bit. But then as there's complicated phenomenology of this power spectrum. Then as you transition down to the soft state, boom, the power disappears and the system goes very quiet. Okay, so that's what's happening there. And finally, this is all X-ray view. You fold in multi-waveband views. You bring in the radio astronomers, bring in infrared astronomers. You find there's jets in these systems that you see in the radio and infrared. And the jets are here on this side of the plot. Here in the hard state, in the so-called intermediate state, we the transition. They hit the jet line. As you pass through the jet line, there's these eruptive, powerful jet outbursts, and then the jet turns off. So there's a complicated again phenomenology associated with the jet physics here. But fundamentally, jets on this side, no jets on this side. Okay, so I want to start off by with this one digging into the aperiodic variability. So I'll worry about this overall outburst cycle in a few minutes, but I want to focus now on just some of the aspects of, for example, this hard state. So this is a gorgeous data set from the NICER observatory. NICER is a large collecting area X-ray facility on the space station. And you can see here, just look, this is seconds here, so this is 16 seconds worth of data. See the count rates we're getting. And this data stream goes on for thousands of seconds. Okay, I mean, this gorgeous. And you can just see the time scale on which we're getting variability here visually in this plot. Now, this is very, first thing is, yes, variability, turbulent system, not a huge surprise, but there's tremendous structure in here if we dig into it. First and foremost, if you just look at the PDF of that emission, and this is actually not that system, this is an old plot from SingSA, it's beautifully log normal. So the PDF of that light curve can be fit by beautiful log normals. So something's going on there. Associated with that, I mean, sort of hand in glove with that, there's a strong RMS flux relationship. The typical RMS variability is small when the system is faint, and it's big when the system is bright. So that's this linear RMS flux relationship. So a lot of this has been attributed to Phil Utley, who's done a huge amount of work on this. So that's the PDF. Going back to the power spectrum, these power spectra are broad. So the things I want to flag here is that look at the frequencies this goes down to. You have appreciable power at 0.1 hertz. That's 10-second timescales coming from the inner regions of the disk, where the light crossing time is measured in tens of milliseconds. So you have, and in fact, all the fundamental timescales are measured on much shorter timescales. So the inner parts of these systems have characteristic variability imprinted in them that is extremely long for their region. The other thing I want to point out here is there's breaks in this power spectrum. I'm going to come back to this with a notion of how we can interpret that break. And then something which, again, could be a whole talk, and I will not mention anymore. There are these nice spikes. There's something in the system that is oscillating, and many of us had many ideas on that, but I won't return to that. And then the final bit of phenomenology before I actually start talking about some connections model is there are non-trivial time lags between different energy bands. So if you look at your spectrum, these spectra, or these data here, for example, it's important to realize that every one of these photons that's come in, we also energy tag. So we have a whole spectral domain attached to this, as well as the time domain. So we can do detailed spectral timing analysis in any way we want. And so we find that if you take two particular bands, for example, in this plot, is 0.2 to 3 kV versus 0.5 to 0.9 kV. Those two bands are time lagged with respect to each other in a way that is Fourier frequency dependent. So you break the light curves up in the Fourier domain, you find that there are phase offsets between particular Fourier components but that phase offset depends upon the Fourier components. There's no single time lag here. There's a whole range of time lags depending upon the Fourier frequency. And the other thing to point out here is, if you go down to low frequencies, so of order, 10 to the minus 2, the time lags are very long, second-long time lags between energy bands. Remembering this is all coming from a tiny, tiny, tiny region that's tens of milliseconds light crossing time. So these very long memories of what's going on here. Okay, that's a very quick dash through phenomenology. How do we interpret this? Well, the framework that we've been using for this so-called propagating fluctuation framework, and this dates back to Lubarsky in the 90s. And the basic idea is that at each radius in the disk, you have a turbulent process that is gating, in a fluctuating way, it's gating the angular momentum transport in the flow. And that's gating the mass accretion rate in the flow. And that's happening at each radius. And then it happens like a conveyor belt. That just, you hand off the fluctuations downwards as you go through the disk, as the system accretes. And then, of course, you get into the central parts, which actually are the parts that are really radiating, especially radiating in the bands you're looking at. And they've already inherited the long time scale, slow variability that will be going on in the outer parts of the disk. And that's how we understand the fact that we're getting very long time scales being imprinted in the emission from the central parts, from the short time scale regions of the disk. That's the basic picture here. As a side note, I've never quite liked the term propagating here, because in no sense can you ever write this down as a wave equation with things passing through. But yeah, it does tend to work like this. So you can set this up in an MHD run, something that Drew Hogg and I did some years ago now. You can do a very vanilla model of a thinnish accretion disk, kept thin with a ad hoc cooling term, and just run it. And then the key here, which is related exactly to one of Omer's final points, to do any kind of time analysis on a simulation, you've got to run it a long, long time, which is the principal barrier here. So at this moment, back in 2016, this is one of the longest runs that we've done. You can generate simulated data. We find, lo and behold, it's log normal. We find power spectra that are reasonable. And this is I won't dig into what this is. This is the coherence function of the emission between two different regions in the disk, or a reference region at 6 gravitational radii, and then some other region out. And you find, lo and behold, that the two separate radii are coherent on frequencies lower than would correspond to 1 over the inflow time between them. So it works exactly as you'd expect for the propagating fluctuation picture. Now, you might think, okay, this makes sense. We have turbulence here. It's the dynamical timescale turbulence that's gating everything. That isn't quite how it seems to work. Take power spectra of the change of the stress, the BRB phi here, in the system. You actually find the main spike in the power spectrum is at much lower frequencies than the dynamical frequency. It's more like dynamical frequency over 10. And if you take the power spectrum of B phi, you find this huge spike at roughly that frequency. And what we are seeing here are the butterfly diagram effects. So if you if you now take a particular radius and you do a space-time diagram in the vertical direction of B phi, you find butterflies here as you're getting bundles of toroidal field forming and floating up or being pushed up in the disk and then reversing and happening. And it's a very generic feature of.
What is the vertical?
That vertical distance in the disk. So it's the theta from theta is 2 pi upwards off the midplane. So this is vertical distance off the disk. So there's this quasi-periodic dynamo cycle process that's going on, generating this field. That seems to be what is driving the fluctuations in the effective angular momentum transport, which is then giving us these features. Now, just to briefly say, you can, with that knowledge, you can then set this up in. We can, relive the 1970s all over again. Put this into a Skoroseniev picture, where we have the, we write down this alpha disk model, just as Omer did last time in the last talk, but now we can make alpha here a stochastic variable. We can drive it on any timescale we choose. We can choose to drive it on this dynamo timescale, and we can actually reproduce at some broad brush most of the behavior we see. So, for example, we can these are model power spectra that we get from that simple stochastic alpha approach, and we lo and behold get a break. That break corresponds to the driving time scale in the emitting part of the disk, in the part of the disk that's principally giving us most of our luminosity, where the actual most of the gravitational energy is released. And so that we can actually just read off what the break frequency is. We find that we've got we've got basically the drive time scale in the break frequency, and just comparing to observed breaks, we get T drive over T dynamical of about 10 to 30, which is in the right range for those dynamo cycles. Okay, now just to briefly, 3 minutes. Okay, we take a brief dash to this. Speculation, down in the soft state, we find the variability goes away. I've always wondered whether we can attach that to somehow killing that dynamo cycle in that state. I don't know how you kill it, but if we can somehow kill the dynamo cycle in that state, then we can do that. Right, in the last 3 minutes, let me quickly come to these cycles. It's very difficult to understand how a system can have hysteresis on weak timescales, given weeks timescales, given all the fundamental timescales in the disk are really, really small. So there's some memory that the disk must have here of where it is in the dynamo cycle. And for a long time, many of us have thought it's basically the generation and destruction of large-scale magnetic flux that might be giving us that memory. And this is another Begelman and Armitage's paper where they've gone through this picture of having magnetic flux generation in a thick flow, in the thick flow, and then when you undergo a state transition, you lose that thick flow, you go to a thin flow, and you lose that flux bundle, and then you regenerate this again. So it's an interesting question whether, if you just look at this slide, can you naturally, from some kind of dynamo process, grow a large-scale field in that thick flow? That's a very important question that I think is still very much out there. This is something that is a subject of a paper that Peyton Rodman, my student in Cambridge, have been working on, where we've set up some, again, very simple vanilla accretion tori, essentially. They're quite thick disks, 0.3 H over R, and then again, run them for a very long time to see if there's some slow growth of the field, can we find it. And the two basic interesting conclusions here, this is the magnetic flux threading the central quotes black hole. So you find that if you start off with we're starting with purely toroidal field. How much time do I have? One. Purely toroidal field. 1 minute. Okay. Then we get a reasonable flux passing through the central the central region. But in fact, we haven't actually changed the average plasma beta very much. We haven't actually generated much magnetic flux. I suspect we've just taken some toroidal field loops and reoriented them, and maybe accreted 1/2 somehow. In the higher beta case, we find maybe a random walk of field lines. There's no evidence yet that these simulations ever forget their initial conditions, which is an interesting question. And no evidence yet for a very strong, obvious generation of large-scale field. Now, I'll put this up and then just stop. This was also looked at by Matthew Liska. On the face of it, and more recently by Jonathan, using the same models. And I think there's actually, in many ways, a broad agreement between our beta 5 run and these runs. And one interesting thing here, which I hadn't quite caught into before the nice analysis by Jonathan, is, of course, what happens to the other flux, the other polarity? Well, in these runs, it literally gets vectored outwards. The outer part of the disk is spreading out, and that carries polarity with it, which suggests that this might work for very small disks, not for big disks. So maybe this could work, for example, for relativistic TDEs, but not for AGN. So, right, let me put my conclusions up and stop. Thank you.
Thanks, Chris. That was great. I have a question that's partially for Charles as well, who may or may not be here.
No, I think Charles had to go. Yeah.
So in Charles's analysis of the time variability in models of M87 in the galactic center, he also finds that there's a lot of variability on timescales of tens of dynamical times. And it's actually associated with the fact that there are spiral waves in the global models whose pattern speed is much less than the local rotation frequency. So I'm just curious whether that plays a similar role. The timescales seem similar. Have you looked at the role of that in the context of the models you've done?
That's interesting. So, I mean, this analysis of those dynamos, the B5 for the dynamo cycles, and then our subsequent analysis, is actually azimuth the average. So these structures are actually, m equals 0 structures. So it's not, in detail, it's not the same as Charles defined, but whether it's just one aspect of a mode structure that is all part of the same physics, I don't think is known.
So is the variability that you're modeling also axisymmetric? Meaning, is it possible that the variabilities, the dynamo cycles are there, but the variability is actually dominated by the spiral features?
It's possible, yeah.
Thanks.
Thank you, Chris. That was an excellent talk, and it was the tutorial for something I knew nothing about before an hour ago. But I wanted to make a connection, which was, it's pretty cool, between what you were talking about, that time variability and these low frequency variations, to Wheely's excellent talk yesterday, and the things that we do in driving turbulence simulations with these oscillating Langevin antennas, which is that although your primary frequency is sort of these hertz and faster oscillations that you see on those nicer observations that you showed, but as you said, for a transform, you see this low power at 0.1 hertz and so forth. Is that that seems to be, and I think this is what you're saying. I hope I'm interpreting it correctly. It's this it's this longer time variability due to variations in accretion flow rate, and it's effectively an envelope of those shorter term oscillations, like the ultimate amplitude of how much, and those vary over time. And again, this is really just a comment about signal processing of time series data, which is exactly the same thing that we have to use to interpret all of what Wheely is talking about, which is that you get these low frequency things, and it doesn't mean that there's an oscillation strictly at that frequency, but that the amplitude of the oscillations is varying at that frequency. And we I don't know, as physicists, we somehow don't know this. And I think that it's canon in sort of signal processing world, but it's, we see things, we see frequencies that don't agree, as you said, those red lines that are up at, their order of magnitude faster than where you see this big peak of some power. And I think that it's important to understand that, there are these longer term variations, but they're not necessarily oscillatory, they're just amplitude variations.
That's right. Yeah, I mean, especially in the context of analyzing simulations more than the real data, one thing that we've got to be very careful of are secular changes in the simulation. I mean, all of these models that we're talking about, we've got a finite amount of matter that's draining away. So there's actually this sort of more or less exponential secular change if you run long enough, and you Fourier transform that. Yes, you get a lot of low frequency power, which is entirely just an artifact of the secular change in the simulation. So that can be less of a problem in the real data, but in the when you're doing the simulations, that's absolutely an issue.
Excellent, thank you.
Great talk, thank you. I wonder if you could say more about how this model for the variability that you developed, like thinking specifically about X-ray binaries, applies to other cases where we're confused about variability, like with Sagittarius A star.
Yeah, so, okay, so for most of the luminous AGN that I spend much of my time worrying about, I think much of all the very nice, complicated things that Owen was talking about, I mean, some of the same physics might be at play. I mean, ostensibly, some of the phenomenology actually is similar once you correct for the different, energy scales and wave bands you're looking at. Sag A star, I mean, that's a whole other category, given both the fact, both its accretion regime it's in this very hot regime. The physics is different. It's probably much more weakly collisional, and then of course the nature of the data we're dealing with now, especially post CHT, is just transformatively different. So we haven't thought, first central question is whether the models that fit EHT actually get these kind of dynamo cycles. And that I'm not actually sure. Elliot, do you know if they've looked at that at all?
I think they tend to be switching magnetically down.
Yeah, but you don't get them. Yeah. So yeah, that would suggest that in those very magnetic dominator systems, the variability might be very, very different.
Hi, fascinating talk. I have one question. Basically, is observational. It's not simulation. Sure. Observational. How often, when you're out in the sky looking, do these anomalies occur? Are they frequent, and do they happen more than once in the same black hole?
That's an excellent question. These outbursts, some system up there is outbursting maybe once a year or so.
So you're talking about someplace out there?
One place in our galaxy.
Once a year.
Is once a year. Sometimes, and they do reoccur. So there are systems now where there have been multiple outbursts from the same system, and sometimes it's a completely new one that we never knew about.
From the same black hole.
From the same black hole.
Oh, okay.
Yeah.
All right.
And then sometimes it's a completely new one that we didn't know about.
How often do you see that from the same black hole? Often or seldom?
Fairly often these days. I mean, we've basically had good data on this since, certainly since the 90s with RXT and even probably before that. So I couldn't tell you off the top of my head exactly what fraction of known systems have been seen to repeat, but it must be quite a high fraction.
Okay, well, thank you.
Been known to repeat.
Okay, Chris, I'm curious. You've discussed a few times the possibility of getting a colloidal field from an internal dynamo process in a thin disk, which is difficult, but I don't know. Is there no possibility that the same phenomena can't be driven by a advected colloidal field?
The interesting question there is in the there's two comments. One is that they then introduce a very strong environment dependence.
Yes.
On the systems you're discussing, and maybe that, I mean,
I understand that
maybe that's reasonable,
unpleasant.
but there's a universality of many of these systems that would be difficult to understand if there was a very, very strong environment dependence. And the other thing is that these X-ray binary cycles, again, which are very, very, very repeatable, whether you could drive that with sort of, I guess, a breathing in and out of a vectored flux is an interesting question. It's not clear, it's not obvious you couldn't. But having a scenario where you can sort of generate the flux in place and then lose it, that might be I don't know. It's an open question.
Okay.
Yeah.
Chris, yes, my question is exactly in this direction. I didn't see that Ethan was. So it's really fascinating that you have the small scale dynamo connected to the fluctuations in the hard state. And then when it goes to the soft state, you might have this transition to the large scale dynamo, right? So you said that you are doing those studies, the last slide that you showed. What is the hypothesis that you have in those, in that study to go into this transition? Do you have to assume omega effects or alpha effect?
So in those models, we don't attempt to model the transition. We're basically, in those models, we're essentially asking the question, in the hotter flow, the thicker flow, if we start off from conditions that have zero colloidal flux, will we naturally, over enough time, grow a colloidal flux that is unipolar, stable in direction? That was the question we were addressing there.
Really?
The next stage would be to see how that behaves through transitions.
Really very interesting. I would like to see the connections with solar dynamo problem because
Absolutely.
Yeah.